So today we're going to be graphing quadratics in factored form. And the idea is that factored form is going to give us the two zeros, the two factors, or the two roots of the equation. And this is going to be different than vertex form because the vertex is found directly between these two roots. And this is based off something called the zero product property. The zero product property says that if this is 0, I don't care what's over here because the whole thing is going to be 0. And likewise, if this factor equals 0, I don't care what's over here because 0 times whatever is still going to be 0. So that's what makes this special. And so I know that if I want my y value to be 0, I only need one or the other to be 0. So that's going to allow me to find what I call my root 1 and my root 2. My root 1 is simply x minus 1. If that equals 0, then it doesn't matter what's over here. So I add my 1 to both sides. I found my first root. So I'm going to plug in a nice point at x equals 1. For my root 2, I say, okay, so x minus 3 is equal to 0. Add 3 to both sides. I get x equals 3. Boom. And so now what I'm looking at is I know that my quadratic is either going to curve down through those points or up through those points. And it could be a really steep up and go very high, or it could just be a little up and be relatively flat. We don't know. So what we're going to need to do is we need to find where the vertex is, which we know is found directly between the two roots. So I'm going to ask myself, what's directly between 1 and 3? Well, 2. And so 2 is what we actually call our axis of symmetry. And that just means that what's on the left is a mirror image of what's on the right. So my axis of symmetry is x is equal to 2. So I just need to know where along this axis, my vertex is going to be somewhere. It might be through this part, it might be through farther down, it might be through somewhere up. So what I'm going to do is I'm going to plug x equals 2 into my equation to find where that graph is. And so I say, okay, to find the vertex, plug in f of 2. And that's going to equal minus 1, minus 3. I'm going to plug my 2 into both spots where there's an x. So 2 minus 1 is going to give me a 1. 2 minus 3 is negative 1. 1 times negative 1 is negative 1. So my vertex is at 2, negative 1. So 2, negative 1. Boom. So I have my graph. Now, we know that when we curve it through, you could graph some more points, but realistically speaking, we know the minimum height, we know the two zeros. The only thing is we could find is the y-intercept, and we'll find that out at a later date. So as long as you can graph the two zeros, the two roots, and the vertex, we're good on graphing quadratics in factored form. So let's try one more. We notice that this one has a negative sign out front. So will that mess up our answers? No. For root 1, I'm going to say x plus 1 is equal to 0. For root 2, x plus 3 is equal to 0. Because I know that if either one of them is 0, 0 times the other thing is going to be flat, which is going to give me some point along this line. So I have an x of negative 1, an x of negative 3. Oh, cool. So this is kind of a mirror image of what we just did. Negative 1, negative 3. And so we know that the vertex is going to be somewhere between these two on this thing called the axis of symmetry. We know it repeats on each side. And so my axis of symmetry is x is negative 2. So what's special about that is that if my vertex exists somewhere at x equals negative 2, I can just plug it in. So let's go ahead and let's do that. Let's find the vertex. So f of negative 2 equals negative plus 1 plus 3. So negative 2 plus 1 and negative 2 plus 3. So negative, it's negative 1, 1. Negative times a negative is going to be a positive 1 times positive 1. We get a vertex at negative 2, comma, 1. Oh, cool. So what we know is that the graph is going to curve up through that point and curve down back in this direction. And so that's a flipped version, and the big indicator is the fact that that negative sign, if we remember our transformations, means that the graph flips. So what I want you to do is I want you to pause the video. I want you to try number 5 and see how you do. Okay, let's give it a shot. I know my root 1 and my root 2. So if I have x minus 2 is 0 and x plus 2 is 0, that means x equals 2 and negative 2. So I have a point 2 and negative 2. Oh. So that must mean if my vertex is directly between them, it's somewhere along this line right there. So now my axis of symmetry is at x equals 0. I just got to plug that in, see what happens. So I'm going to do that. So if I plug in f of 0, and I like this because 0 is always easy to work with. 0 minus 2, 0 plus 2. Now that's going to be a negative 2 times a positive 2, which is going to be a negative 4. So now my coordinate for my vertex is at 0, negative 4. Right there. So what we have is we have a quadratic just like that. Perfect. So let's try something a little different. What happens if I don't have two complete factors? Well, it's a little deceiving because we do. I know I have one of my roots, my root 1, is going to be where x plus 4 is equal to 0. But what's going on with that? Well, I could look at it as what happens if I put that in parentheses. Well, there's my other root. So root 2 is just where negative x is equal to 0. Because if either one of these is equal to 0, the entire other thing is. Which means that if x equals negative 4, I could plug that in. Negative 4 plus 4 is 0. That obliterates everything. If x was 0, plug that in. Negative 0 is 0. 0 times whatever that is, I don't even care. 0 times that is 0. So those are my two roots, at 0 and at negative 4. Which means that my axis of symmetry is somewhere where x is negative 2 again. So we're going to go ahead and we're going to plug in f of negative 2. So it equals a negative 2 times negative 2 plus 4. And I know a negative 2 is going to give me a positive 2. Negative 2 plus 4 is going to give me a positive 2. Positive 2 and positive 2 is going to give me a positive 4. So now my vertex is going to be found at negative 2, comma, 4. We have 2, 4. Oh, hey, So I notice again that if I have a negative leading out front there, I know that my quadratic is going to be upside down. Yeah. Should have a steadier hand. Cool. And so these last two are what happens if we have fractions. Now, realistically with this one, I designed it a little bit more difficult than it should be, but we're going to use it and we're going to get the point across. So what we know is we know our two roots. Root 1 is where 2x plus 3 is 0, and the other one is where 4x plus 3 is 0. I know if I subtract the 3, 2x is negative 3, divide by 2, x is negative 3 halves. I know at negative 3 halves, I have a root. It's not quite at 2, it's kind of in between two values. For my other root, 4x is negative 3, x is negative 3 fourths. And so this one is right there. And now what a lot of people would be tempted to do is they'd say, hey, it's going to be 1, because 1 is between those two, right? Well, remember, this is basically a quarter away from negative 1, and that's a half away from negative 1. So it's not balanced. So what we're going to have to do is we're going to have to find what is directly between those 2 points. And we do that by finding the average. Let's go ahead and figure out what the average of these 2 points are. So to find the average, what we call x bar, is we take negative 3 halves and we add it to negative 3 fourths, and we divide it in half. So we know the fact that these need to have a common denominator, which means that I need to have negative 6 fourths minus 3 fourths, all divided by 2. So 6 fourths minus 3 fourths is negative 9 fourths, all divided by 2. So I'm going to keep, change, flip, negative 9 fourths times 1/2, which is going to give me a negative 9/8. So that is where my axis of symmetry lies. At this really awkward value of negative 9/8. It's not pretty, but it works. Now, somewhere along that line is going to be my vertex. So I'm going to plug that in and say, to find my vertex, I'm going to take f of negative 9/8 equals 2 plus 3, 4 plus 3. And we see that this is going to get a little dirty. That's okay. Negative 9/8, negative 9/8. So our first step is we're going to multiply this. I know that that's going to turn into an 18 divided by 8, which is going to reduce because 2 divided by 8 will reduce. That'll turn that into a 4. So that'll be a negative 9 fourths plus 3. 4 divided by 8 is going to be 1/2, so it's going to turn that into a 2. So negative 9 halves plus 3. I'll come up over here into this box to give me some room. I know that to add these two, I need them to be common. So that's going to be a negative 9 fourths plus, well, if I turn 3 into a fourth, that's going to be 12 fourths. And over here, if I turn 3 into a half, that's going to be negative 9 halves plus 6 halves. So getting these together, I have 3 fourths times negative 3 fourths, which is going to give me a negative 9/8. So my f of negative 9/8, negative 9/8. Well, that's an interesting vertex. Negative 9/8, negative 9/8. That's a very skinny vertex. like I said, the only thing that we probably could find after this is where the y-intercept is. That might be an important point. But as of right now, we're just focusing on graphing these 2 points and graphing the vertex to find that curve. We know this is a very skinny parabola. This new piece of information of finding the mean, finding that middle piece, is the only new part. So what I want you to do, last one isn't quite as dirty. Pause the video, see if you can solve it, unpause it when you're done. Okay. So if I find root 1 and root 2, root 1 is at 2x minus 3 is 0. This one is 2x plus 3 is 0. So I add 3 and divide by 2. Subtract 3 and divide by 2. Boop, boop. So I know I have, let's see, 3 halves, which is about 1.5, and negative 3 halves, which is negative 1.5. Well, I know those are on opposite sides of my origin line, or my y-axis. So my axis of symmetry is where x is equal to 0. But just in case, let's say it was an example like this. How do I find the mean or the average? Well, I know that my x bar is 3 halves plus a negative 3 halves, all divided by 2. And this is much simpler. We know that 3 halves minus 3 halves is going to be a 0 divided by 2, which is a 0. So that's an easy way to figure out this if it looks like it's going to be a little difficult to solve. So to find my vertex, I just plug it in. So f of 0, which we always like because zeros work really well. Two times 0 minus 3 times 2 times 0 plus 3. 2 times 0 cancels out, so it's just going to be a negative 3 times positive 3, or negative 9. That was much easier. And so unfortunately I didn't draw this to scale, so I can't fit a negative 9 on here. So what I'm going to have to do is I'm going to have to go ahead, my x's have to be by 1s because I've already plotted those points, but I'm going to draw my y by 2s. That's going to allow me to stick 2, 4, 6, 8, 9. So what we get is we get a quadratic that looks like that. There we go. So what we're working on today is graphing a quadratic in standard form. Now, this is typically done because quadratics are going to come in this simplified format. We're not going to see them in factored form or vertex form too terribly often. So we need to know how to work with this, and there's a couple different ways. You can either A, learn a couple different formula on where we find the vertex and how we find the roots and things like that. I like to see, can we factor this equation? Because we're going to learn about something called the quadratic equation later on, but most of these are going to be easily hand factored. So we're going to pull out an old trick that we have where we're going to factor this into the 2 roots. Our first trick is we take the first and the last numbers and we multiply them together. So I have a 1 times a 3, which is going to give me a 3. And because that's a positive 3, I know I'm going to be finding the sum. And then what I do is I take a list of all possible factors of 3, which the only one I have is 1 times 3. And I'm going to see which set of factors add up to a 4. And like I said, conveniently speaking, this one does add up to 4. So I'm going to be able to rewrite this expression as an x squared minus 1x minus 3x plus 3. What I've done is I've split the 4 into 2 terms. And what this allows me to do is this allows me to move forward and pull out my GCFs. Pull out GCF of x and of negative 3. Anytime I have a negative leading coefficient, I'm going to pull it out with it, which means that if I pull out an x and a negative 3, so I have x divided by, or x squared divided by x, negative 1x divided by x, negative 3x divided by x, so that's boop, x, and then minus 1. And what we notice is that both terms, now that I've plotted the GCF, both share an x minus 1. So I'm going to factor that out. X minus 1 times x minus 3. And this is really what I'm after, is this piece right here. Because as we've seen previously, these two factors allow us to graph our quadratic. I know that I'm going to have a point at 1, and I know I'm going to have a point at 3. If you don't remember how that happened, well, we took two roots. We said root 1 was when x minus 1 was equal to 0, which we add 1 to both sides. There's our first root. And for our second root, we know that we took x minus 3 and set that equal to 0. Add 3 to both sides, and I get my other root. So root 1, root 2. The second thing that we went over was we said, hey, if I found my two roots, my vertex, that maximum or minimum point, is going to be directly between them. And I know that's going to happen somewhere at x equals 2. I don't know how high, I don't know how low. The only way to actually find that out is to take my x equals 2 and plug it in. So I'm going to plug in f of 2 equals squared minus 4. I'm going to plug a 2 wherever I see an x. And then I'm just going to go ahead and solve it. So 4 minus 8 plus 3. 4 minus 8 is going to be negative 4. Plus 3 is going to be negative 1. And that's actually where my vertex is at 2, negative 1. And that allows me to graph that right there. Now the cool thing is I could have plugged it into this as well. If I plugged in a 2, that would be 2 minus 1. 2 minus 3 would be negative 1. So 1 times negative 1 is still going to get me the same answer. So plug it into whichever one you think is easier to do. So let's try that again. For question 3, we're going to do the same thing. I'm going to take that first number and that last number, and I'm going to multiply them together. Negative 1 times negative 8 gives me a positive 8, which means I'm finding the sum of these factors. Now, this set of factors is a little larger. 1 times 8 equals 8. 2 times 4 also equals 8. 3 doesn't work, 4 doesn't work, and so we've done what I've called completing the loop. I'm going to add them up. 1 and 8 make 9, 2 and 4 make 6. And I'm looking for a set that makes 6 right there. So I'm going to split my 6 into a 2 and a 4. And we know this is because that will allow me to recombine later on and get a negative 6. And then, let's stay consistent, I'll keep with purple. To factor these things, again, if I have a negative leading coefficient, whatever I pull out is going to be negative. I have an x here and a 4 here, which means that if I have a negative x and a negative 4, it's going to change both those signs and give me an x plus 2. This is going to change both those signs and give me an x plus 2. And because those are the same, I'm going to pull out an x plus 2 and get that. And again, like we've said, this is what we're after, is we want to get an equation to where we can very easily look at what's going on. Well, if I were to solve for that, I would get a negative 2. Let's see, add the 4. That'd be a negative 4. Again, if you actually want to see it written out, root 1, root 2, x plus 2 is 0. Subtract the 2. Boom. Negative x minus 4 is 0. Negative x is 4. X is negative 4. Boom. There we go. And so this time, I'm going to take that middle value, and instead of plugging in the original one, I'm going to plug it into my new equation. And I'm going to say, okay, f of, let's see, this is -1, -2, -3. I'm going to plug it into right here. So -3, -3. -3 plus 2 is -1. Negative makes it a +3, minus 4 is -1. So my f of -3 is +1. Tells me my vertex is right here. So my quadratic is going to curve just like that. Perfect. And so with this one's a little trickier. So take a second and think, how am I going to split that? How am I going to graph that and find the two roots? Well, there's no b term by the looks of it. And what we'll actually realize is there is a b term. Even though I don't see that middle x, it exists. It's just got a coefficient of 0. Because 0 times anything is 0, and I would skip writing that if I were the problem. So that tells me I'm looking for whatever 1 times -4 is, which is a -4. In this case, I'm finding the difference. I want to find a difference of 0. So 1 times 4 is 4, and 2 times 2 is 4. Well, the difference between 1 and 4 is 3, and the difference here is 0. So I'm actually going to be using the 2 and the 2. And because I'm taking the difference, they have different signs. So x squared plus 2x minus 2x. And we see that these would actually cancel out, and this would simplify down to our original question. Pull out my GCFs. I have a leading negative. This is going to give me an x plus 2, x plus 2, which means I can pull out that x plus 2 and get an x minus 2 left over. And this is what we're after. That's going to tell me that I have a root at -2 and a root at +2. I know that my vertex is going to be somewhere here in the middle. And that middle is going to be x equals 0, so I'm going to plug that into my equation. And because it's 0, I'm going to plug it into the original one again, because I know that that's going to be much easier for us to handle. Yep. Because if I plug in a 0 squared, it's literally just my last term, my constant. Perfect. So that will give me the ability to graph just like that. There we go. Let's try something a little more advanced. So what happens if we have, with these new problems, something where I don't have a c? Originally I didn't have that middle term, I didn't have my b, but now I don't have that constant that's just on the right. Well, these are actually going to be a little easier to work because immediately I notice that somebody has distributed an x. So I can divide out an x out of the expression, which is going to give me the thing that I seek without having to factor it any further. I just boop, boop, there we go. I have my two roots. So root 1 is where x is equal to 0, and root 2 is where x minus 4 is equal to 0, which means that x must be equal to 4. So I have those two values to plug in, which is going to look like this and this. Perfect. And if I know I have two values at 0, and at 4, I know that my axis of symmetry, or that line where my vertex is going to be right in the middle where x is equal to 2. And so all I need to do is plug in f of, I can either plug 2 into this factored form or in the top form. I'm going to plug it into the top one myself. So plug in a 2. Let's see what we get. Well, 2 squared is 4 minus 8. That is negative 4. Draw my negative sign a little bigger right there. So boom, I have a vertex right there. So I know that my graph, curve, curve, and curve. So I have f of x is equal to x squared minus 4x. Perfect. Looks like that. And as we move forward, really just what we're getting into is some other variations of it. If you have something with an actual coefficient, the process is no different. You're just going to have a larger set of numbers that you're pulling from. Also, with that larger coefficient, what we'll learn later on is that means the graph is going to be much skinnier because the graph is going to be stretched. But we'll see that from our resulting graph. So we're going to work it out with 4 times 15, which is 15. And actually, I think this is a good idea. I'm going to pause it right there. Why don't you try the next 2 questions and unpause the video when you're done to see how you do. I think this is a good chance to try those out. Okay, so now we're going to go ahead and resume. Kind of already led you along here where I said, okay, we're multiplying the first and the last numbers, which is going to give us, okay, well, I kind of asked you to pause there on an interesting note because 4 times 15 is not 15, it is 60. So a lot of you are probably shaking your heads, saying things to the screen because, yeah, you were trying to get 15 to work, which would make 16, and your graph's going to be completely different. Well, so that's actually going to be 4 times 15 is going to be 60. So what I want you to do is I want you to take a pause in this video, and I want you to take factors of 60 and see if you can't finish this out, and try the next one as well. I think this is a good chance to try out our skills. Okay, so now that you've unpaused the video, let's see how you did. Well, my factors of 60 this time are quite lengthy. I got 1 and 60, 2 and 30, 3 and 20, I have 4 and 15, 5 and 12, 6 and 10. 7 doesn't work, 8 doesn't work, 9 doesn't work, 10 has completed the loop. So I know with that plus 60, I'm going to be looking at sums. So 61, 32, 23, 19, 17, and 16. Ooh, that means the last ones is what I actually needed. So I'm going to go ahead and I'm going to plug those in. I'm actually going to draw this down here so it gives me a little bit more room. So 4x squared plus 6x plus 10x plus 15. And that's going to allow me to pull out 2 GCFs. Over here it looks like a 2x. Over here it looks like a 5. So 2x plus 5. Once I divide those things out, that's going to give me a 2x plus 3, 2x plus 3, perfect, 2x plus 3. And then my other factor is going to be 2x plus 5. Awesome. And so that means that my 2 roots are going to be, I'm actually going to do that up here, root 1, is going to be where 2x plus 3 is equal to 0, and my root 2 is going to be where 2x plus 5 is equal to 0. Separate that off a little bit. So if I subtract my 3 and divide by 2, that's going to give me an x equals subtracted 3 divided by 2. If I subtract my 5 and divide by 2, I get those. So my 2 roots. Negative 3 halves, which is about 1.5, and negative 5 halves, which is right there. Awesome. And so the next thing I'm going to do is I'm going to have to find where the vertex is. And luckily for us, directly between -3 and -5/2 is going to be -4/2, also known as -2. So let's go ahead and plug that -2 into our function, either up here or down here. And so I'm going to plug it into the factored form, just because I want to be different. I want to show different things. So f of equals, oops, sorry, that's a 2, and then I open my parentheses, plus 3, 2, plus 5. I'm going to plug in my -2. Can't really tell that right there. That's a 2 times -2. It's going to give me a -4 plus 3, -4 plus 5. -1 times +1, which is -1. So -2, -1. Perfect. And so we notice that, again, we mentioned earlier that that 4 is going to be stretching it. This is a much tighter graph. It's not that nice spread out graph that we have right there. This is very tightly bound. So we're going to play some more around with that in a later lesson. And then the last one, this is another one of those where I'm missing that middle term. So I'm going to be looking for factors of 4 and -9, which is a -36, which in this case make a difference because of that negative sign. Means I'm going to be subtracting the two numbers instead of like we did up here where we added them. So I have 1 and 36, 2 and 18, 3 and 12, 4 and 9, 5 doesn't work, 6 and 6, and that completes the loop. So if I need a difference of 0, I need the same number, so I'm not even going to worry about those. I know it's going to be my 6's. So if I have a 4x squared plus 6x minus 6x minus 9, that's a good place to start. So 2x, because I have a leading negative, 3. So 2x and -3. And if I divide those by 2, I get a 2x plus 3. Over here, if I change the sign, that also becomes a 2x, and that now changes to a plus 3. Hey, perfect. So I have a 2x plus 3 as one factor, and for my other factor, I have a 2x minus 3. That's cool. So I have the same thing. This is what we're going to call a conjugate. So we'll see more about conjugates later on. And so my two roots, root 1 is where 2x plus 3 is equal to 0, and root 2 is where 2x minus 3 is equal to 0. So let's see. If I subtract 3 and divide by 2, there's 1. If I add the 3 and divide by 2, there's the other one. So I have -3/2, and I have +3/2. So -1.5 and +1.5. Awesome. And those look like, to me, I don't know about to you, but those look like they're on opposite sides of my y-axis. So I know that vertex is going to be somewhere where x is going to be equal to 0. So I'm going to plug 0 in up here because this looks like it might be a little more work. Not much, but a little. 4 times squared minus 9. And if I plug in that 0, well, that made that easy work. F of 0 is -9, which, unfortunately, on my 1-by-1 graph, I'm going to have to change things up a little bit. I've already graphed my x's, so my x is going to stay by 1s, but in order to fit my y on there, I'm going to have to make my y by 2s. So now it's 2, 4, 6, 8, 9. There we go. Perfect. And there we go.